Hello guys, thank you for stopping by again. In this video we are going to be drawing the shear force and bending moment diagram for the beam we resolved here some time ago. If you are joining us for the first time, kindly check the description section of this video to get a link to the video where we analyzed the support reactions, and that will eventually help you cope with this one that we're about to solve now. In drawing the shear force and bending moment diagram, the first thing that should come to your mind is to get the expressions. Those expressions are your guide to how the drawing is going to look like, or the shape. To start with, we are going to be cutting section at every point labeled in this beam. We have A, B, C to G. So at every point, we will cut a section and analyze it to see the nature of the shear force and bending moment diagram at those points. The first place we're going to cut the section is between A and B. When you cut a section here, you cut the distance x, because you don't actually know where you're cutting the section if it's exactly at 3 meters away from point A. That is why down here we have 0 less than or equal to x less than or equal to 3. So it means that for every expression that we're going to get here, it only exists from this point A to point B. When you cut the section, you are going to have a moment and also this vertical force. The first we are going to do is the shear force expression. Then one could ask, what is shear force? Shear force is just the summation of the vertical forces. In this section that we have cut, what are the vertical forces we have here? We have 18.3 kilonewton and we have the V alpha. While 18.3 kilonewton is going up, V alpha is coming down. And don't forget, we always say let upward force be equal to downward force. But that is exactly what we're going to do here. At x equal to 0, that is at this initial point, at point A, you have only one vertical force. Therefore, the shear force at that particular point is equal to 18.3 kilonewton, because that is the only vertical force at that point. Then at x equal to 3, we have that V alpha is equal to minus 31.7 kilonewton. Now look at it this way. You know we have 18.3 kilonewton that is going up, and at 3 meters, that means it's exactly under the point load 50 kilonewton. So if this force VA goes up till it gets to this point where you have 50 kilonewton, the magnitude of 50 kilonewton is above that of 18.3 kilonewton. So it will push it down to minus 31.7 kilonewton. That is 18.3 that is going up minus 50 kilonewton that is coming down. That is how we got minus 31.7 kilonewton. When we draw the shape, you see how it looks like. But it's not far from what I have explained here. For the bending moment expression, you see this moment is in anti-clockwise direction. Whenever you cut a section, for easier clarity, always put the moment in this direction, so that whatever that is happening here will be counter-reacted with the one which you have assigned. So we have M alpha, which is the moment moving anti-clockwise direction, and this 18.3 kilonewton, if take moment at this particular point, this 18.3 kilonewton will move in a clockwise direction. Like we did in the previous video, we said let the clockwise turning moment be equal to anti-clockwise turning moment. Therefore, 18.3 kilonewton is a clockwise turning moment, whereas M alpha is anti-clockwise. So it will be M alpha is equal to 18.3 multiplied by the distance which it will cover, and the distance is x. Always remember that moment is force times distance. So the expression gives us M alpha is equal to 18.3x. At x equal to 0, that is at the initial point, what then is the nature of the moment there? Then you substitute 0 for x, and you have that your moment is equal to 0. But at x equals to 3, that is under the point load 50 kilonewton. You substitute 3 for x in the expression, you now have that moment is equal to 54.9 kilonewton meter. That is the nature of the moment under the point load 50 kilonewton. With this, we are done with this particular session. I'm going to cut another session. We will cut another session at exactly point C. taking the second section, that is at joint C, you see that we have this vertical force, we have another vertical force 50 kilonewton, and so you know from point B to where you are taking the section, you don't know the distance because you don't know exactly where you are cutting this section. You don't know if it is at 3 meters away from joint B. Use X to represent it because you don't actually know the distance from this point to where you cut the section. So that is why you represent with X. For the V alpha, which represents the shear force at every section, I will go again by the summation of the vertical forces. You know, V alpha is going down, so the one that is going down should be equal to the one that is going up. So we say V alpha plus 50 kilonewton, which is going down, also should be equal to the one that is going up. That is why we have V alpha. When the 50 kilonewton force crosses sign of equality, it becomes negative. That's why we have V alpha is equal to 18.3, which is going up, minus 50 kilonewton. That will give us V alpha is equal to minus 31.7 kilonewton. So it is negative. Therefore, at point C, the shear force will go below this beam to the negative sign. You know, when you're plotting graph, your upward side is positive, downward side is negative. So the same thing applies here. For the moment at this particular section, we see that our moment is turning in anti-clockwise direction. And when you take a moment at this particular point where you cut the section, the VA, which is 18.3 kilonewton, will turn in a clockwise direction, whereas 50 kilonewton will turn in anti-clockwise direction. That is why we have M alpha is equals to 18.3. This 18.3, what distance will it cover from here to where you are taking the moment? So that is the distance of 3 meters plus X. Remember, I told us that we don't know what the X is. So 18.3 will cover a distance of 3 plus X. That is why we have 18.3 into 3 plus X. Then this 50 kilonewton will move in anti-clockwise direction. So it is negative 50 multiplied by the distance, which is X. When you play around with that, you have that M alpha is equals to 54.9 minus 31.7X. This is the expression for the bending moment. At X equal to 0 is actually under point B. You have that M alpha is equals to 54.9 kilonewton meter, which is the same answer with what we got in the other section, 54.9 kilonewton. So if you solve this and at that same point you have different answer, it means that your expressions are wrong. Then at X equals to 3 meters, that is the distance from here to where you cut your section. If it is 3 meters, your M alpha is going to be equal to minus 40.2 kilonewton meter. It's negative now. Hope you got that. So these two that we have solved, let's try drawing the shear force and bending moment diagram so that as we proceed, we keep adding to the diagram. So in the shear force and bending moment diagram, we have drawn the lines and we have also labeled all the joints like we had in the question where we have A, B, C to G. Let's also go back to this point. For the shear force expression, when we solved at the first joint, we got that V alpha is equals to 18.3 kilonewton at X equal to 0. So let's draw that for the shear force. So this is point A, which is at the point where X is equal to 0. And we have 18.3, which is positive. So we're going to draw a line in a positive direction. I will stop at a point where we feel it represents 18.3 kilonewton. So we'll have this. Let's assume here is the 18.3 kilonewton. For the fact that this is a point load, it will maintain that 18.3 kilonewton till it gets to the next joint. So it will go like this. The next joint is joint B. Now let's look at joint B and know what exactly happened at joint B. At joint B, that is at X equals to 3, we have minus 31.7 kilonewton. Therefore, since it is negative, our line is going to come down below to where we think it should be our negative 31.7 kilonewton. So it will go this way. So let's assume here is our negative 31.7 kilonewton. Remember, between point B to point C is still a point load. So this level of negative 31.7 kilonewton will be maintained till the next joint. This is joint C. You stop here. And now let's look at what happened at joint C. At joint C, our V alpha never changed. So it's minus 31.7 kilonewton. Remember, you're not going to put negative at the 31.7 kilonewton again. For the fact that the diagram comes downwards shows that it is negative already. For the bending moment diagram, let's start with the first expression. In the first expression, our M alpha at point 0 is equal to 0. So at the beginning, we are going to have 0. Now let's look at point B. At point B, that is at our x equals to 3. We have M to be equals to 54.9 kilonewton meter. It is going to go like a triangle because we have point load there, not UDL. It's positive, so it will go this way. At point, this is point B, so we'll stop here. Remember, some other persons can decide to use upward side as the negative and downward side as the positive. But in this video, we are using upward side as positive, the same way we did in the shear force diagram. At joint C, when x is equals to 3 meter, we have that M alpha is equals to minus 40.2 kilonewton meter. So at this point, it went down to the negative side. So at that negative side, it will maintain that same triangular shape to the point C, because between this point A to C, what we'll have acting there is the point load. So it will go this way. Remember, this one will come downwards because it wants to change sign to negative side. It will go to a point where we are confused that we have negative 40.2 kilonewton. You will connect it in a triangular form to this point C, like I have explained earlier, because we have a point load acting within this region. So that is it for the expression that we have done so far. Now let's continue the expression at point D. We are going to combine joint D and joint E together. We have that at C, V is equals to 49.9 kilonewton. That is at this point. So how was that gotten? It was simply 18.3, which is going up, minus 50 kilonewton, which is coming down, then plus 81.6 kilonewton, which is going up. That's how we got 49.9 kilonewton. Make sure that is well represented in the shear force diagram. We know that in the expression we have a 49.9 kilonewton. It means that it's going to go up far above 18.3 kilonewton, because 49 kilonewton is above 18.3 kilonewton. So we'll draw our line and extend it upward side. Then we'll go back to the expression and we'll continue from where we stopped. Also, for the expression, we have V alpha is equals to this 18.3 kilonewton plus 81.6 kilonewton, which is going up, plus 81.6 kilonewton, which is going up, minus 50 kilonewton, which is coming down, minus another force acting as a result of the UDL, which is 30 multiplied by the span at which the UDL will act. Therefore, we have 49.9 minus 30x. Then at x equals to 2, what is our shear force? That is under point D. We have that shear force at x equals to 2 is minus 10.1 kilonewton. Then at x equals to 4, we have that V alpha, which is the shear force, is minus 70.1 kilonewton. So the shear force diagram will continue in the same direction without changing either negative or positive till we get to minus 70.1 kilonewton. Let's represent that in our diagram. So for the fact that it is UDL, is going to maintain a straight line, and the straight line will pass through. So don't forget, at x equals to 4 meter is exactly under point E. So we are going to extend our shear force diagram from point C to point E. There's no need considering the point D, which gave us minus 10.1 kilonewton again, since it tends in the same direction. We extend that to a point under E. And remember, it should go far below 31.7 kilonewton, because what we're talking about is negative 70. So let's assume it is here. Then we'll label it. We go again for the bending moment expression. We have 18.3 kilonewton, which will cover a distance of from this point to this point, and that is 6 meter plus whatever the value of x is. Then we have another 50 kilonewton, which will move in anti-clockwise direction. Therefore, it's going to be negative. Multiply by the distance which it will cover, and that is 3 meter plus x. That's why we have minus 50 into x plus 3. Also, we have 81.6 kilonewton, which will cover a distance of x to where we're taking the moment, and that's why we have 18.6 multiplied by x. And it is positive because it is positive because it will turn in a clockwise direction. Then for the UDL, don't forget that UDL acts at the center. So the magnitude of the UDL is 30 kilonewton per meter as indicated in the question, and we multiply that with the span, which is x, then multiply by half the span, because I've already told us that it will act at the center. So half the span shows the center where it will act from. That's why we have x over 2. When we play around with that, we'll have the expression as m alpha is equals to minus 15x squared plus 49.9x minus 40.2. Then at x equal to 0, at x equal to 0 will be at this point C. We have that m alpha is equals to minus 40.2 kilonewton meter, which must correspond with what we got earlier to show that our expression is right. That is 40.2 kilonewton. We are going to get the turning point, because we all know that when we have UDL, the bending moment diagram is expected to go like a curve. So at what point will the curve be maximum? Like we all know from the knowledge of differentiation that the turning point will be when dy dx is equal to 0. We differentiate the expression for the bending moment, and that will give us minus 30x plus 49.9. Equate the dy dx to 0, and we have the value of x to be 1.66 meter. In that expression for the bending moment, we are going to substitute the value of x into the equation, and after that we have that m alpha is equals to 1.466 kilonewton meter. That is our turning point. At point D, we have that x is equals to 2 meter, because from this point C to point D is 2 meter. Bending moment expression there, when you substitute x to be 2, will give us minus 0.4 kilonewton meter. This value is supposed to be 0 because there is no moment at the hinge, but we're having minus 0.4 kilonewton meter because of the approximation that we have done so far. So had it been we didn't approximate, we're supposed to have 0 because moment at the hinge should be 0. Then at x equals to 4 meter, we have that moment is equals to minus 80.6 kilonewton meter. And at x equals to 4 meter is exactly under support E. So at that support, the moment is minus 80.6 kilonewton meter. Now let's try to represent what we have gotten in the bending moment diagram. Remember, this one is going this way, and it's going to turn at the value that we got, which is at 1.466 kilonewton meter. It will curve this way, and here it will start tending towards 0 because the moment there is 0. That is under point D. Don't forget it continued, and then at this point it's going to be curved also, because we have UDL there, and it will curve to where we have the minus 80.6 kilonewton. Then let's stop at point E and get the other expression so that we know how it will move. Label the values of your moment at different points. Here we got 54.9 kilonewton meter. Here we got 42.2 kilonewton meter. Remember, it was negative, that is why it's downward. Then here we have the turning point to be 1.466 kilonewton meter. At this support we got 80.6 kilonewton meter. Now let's continue the expression to get the remaining side. Remember, we are done with joint E. Instead of us to continue in the same direction, you know this is getting too long and the equation will be long as well. We decided to come from the other end. Having known that we're going to have the same answer, it's still not bad to come from the other end. Just that the difference is that our V alpha, which is the shear force, instead of pointing downwards like the previous ones that we did, it will now point upwards. So coming this way, we have that V is equal to minus 20 plus 20x. Remember, it is UDL. So the support at point G, which is VG, when we calculated from the previous video, we got 20 kilonewton. So if you want to know how we got the reaction, maybe you've not watched the previous video, don't forget to check the description section of this video. The link will be dropped there. So you know that this 20 kilonewton is going up, and this V alpha is going up as well. That is why we have V alpha plus 20 kilonewton. And another 20, when it crosses the sign of equality, it becomes negative. That is why it's showing minus 20. This UDL is moving in opposite direction to these two other forces. That is why we have 20 and it's positive multiplied by x. The x is the span at which the UDL is acting. Then at x equal to 0, we have V alpha to be equal to minus 20 kilonewton. So at this particular point G, our shear force is negative 20 kilonewton. At x equals to 4 meter, V is equals to 60 kilonewton. So if you substitute for x in this equation, you have 60 kilonewton. Therefore, can we draw this shape and see how it looks like before we continue the expression? So let's go down there. Remember, we have minus 20 here. So let's assume our minus 20 will be somewhere around this point. Don't forget that at x equals to 4, which is this point E, we got our answer to be 60 kilonewton, and it is positive. So we're going to move from this point to where we think should be our 60 kilonewton. Don't forget that the 60 kilonewton that we got from the expression is positive. So our answer will tend towards our positive side. So your 60 point should be above 49.9 kilonewton. So it means that at this point we have 60 kilonewton. Here we have minus 20. Let's label that. With this, we are done with the shear force diagram. Let's continue with the bending moment. For the bending moment expression, we have 20 kilonewton, which will move in anti-clockwise direction. We have M alpha turning in a clockwise direction, and we have this UDL, which will also turn in a clockwise direction. So M alpha and this UDL will turn in a clockwise direction, whereas 20 kilonewton turn in anti-clockwise direction. So we're going to have M alpha is equal to 20, which will cover a distance of x, then minus 20 multiplied by the span of the UDL, which is x, multiplied by x over 2, like we did in the previous UDL, to have minus 10x squared plus 20x as the expression for the bending moment. Then at x equals to 0, our moment is equal to 0. That means at this point G, the moment is 0. At the turning point will be when dy dx is equal to 0. When we differentiate this moment expression, we're going to have minus 20x plus 20. Then you equate dy dx to 0 to have the value of x to be 1. When we substitute the value of x in the bending moment expression, we have that moment is equals to 10 kilonewton meter. At x equals to 4 meter, that is at point E, we have that moment is equals to 80 kilonewton meter. Remember, when we solved from the other end, we got 80.6 kilonewton meter. So this difference of 0.6 is as a result of approximation. Now let's try to represent that in our bending moment diagram. So don't forget, here we have the turning point to be 10 kilonewton meter, and it will pass through point F because we have hinge at point F and moment at the hinge should be equal to 0. It will curve this way to point E. So this is all about the shear force and bending moment diagram.